not much calculations are there, but you have to just uh, practice it. Just practice it. Okay. Otherwise, it is very difficult. So yesterday, what we have done, just we have derived the expression for black body radiation. What is how much radiation is emitting from the black body? We have derived expression using Planck. Okay, Planck's radiation law. Okay, Planck's whatever you Planck's derived the expression. We have solved that. We have derived again. So just if you heat the black body, radiation will emit from the black body because the atoms get some thermal energy. They will vibrate to and forth and release the energy. That energy we have estimated using equation. Okay, that is yesterday we got expression. Did you remember that expression? No. Are you able to clearly see my notes? This one note.
Yes,
My
sir.
pen.
Yes, sir.
Clearly
Yes,
visible.
sir.
Okay. Okay. If it is suppose if you are not clearly see, sometime you can zoom it. You can clearly see that one. Your screen, mobile screen is a little bit smaller. No? That's why. Okay. So yesterday we have derived expression for. So as simple as suppose there is a black body. Okay. There is a black body. We have heated this black body. Okay. We have heated this one. Means that is we have given some temperature to this black body. So whatever atoms here, they are getting some thermal energy. They vibrated or they move to and fro. They make a oscillations and they release the energy from the black body. Okay, from this black body we kept a emitter, and that is experimental. Theoretically, what we have done yesterday, that is the whatever emitted radiation from the black body we have estimated using Planck's radiation law. Okay, that is E of nu d nu is equal 8 pi nu square or nu cube, right?
Cube,
Nu
sir.
cube, nu cube or square. What is that?
Cube, sir.
Cube only, right? Okay, good. And 1 by e to the power of h nu by kt minus 1. Okay, this is the expression for black body radiation. Okay, emitted radiation from the black body. Okay, now this is E of nu means what? In terms of this energy density is depending on frequency. Energy density is depending on, okay, as a function of frequency. Okay, now we will convert this equation into in terms of wavelength. Okay, how we will convert? Just we will write this expression E of lambda d lambda, that is in terms of wavelength. This is nu means frequency, lambda means wavelength. Okay, now we have to convert here. Lambda is equal to what we know. What is the lambda is called?
H by
C by lambda, right? Very good.
C
Okay,
by the.
C by lambda. Sorry, this is nu is called C by lambda. Sorry. Okay, C nu is called C by lambda. But here you can directly whatever. Please mute. Someone is. Please mute. Okay, thank you. Okay, suppose nu is there here. You substitute directly C by lambda. Here du nu also there. So just you derive this expression. D nu means what you will get here. What is the derivation of this C by lambda as a function with
C
respect?
nu.
Minus C by lambda square into
Yes, C by lambda square into.
D lambda.
Yes, that's good. Who is that? May I know name? Hello?
Yes, sir.
Who is? What is your name?
Venkatesh, sir.
Venkatesh. Okay, good. Thank you. Okay, this is the expression we have got. Okay, just you substitute nu is equal C by lambda here, and 8 pi nu means 8 pi h is there, right? Here h is there. Okay, 8 pi h h is there, right? Okay, h is there. C by lambda q and c cube here, and 1 by e to the power of hc by lambda kt. I'm writing direct minus 1. Here du nu means minus c by lambda square d lambda. Okay, right? Now you simplify this expression. 8 pi h c cube will cancel out, right? Okay, 8 pi h here lambda nu is equal c by lambda, right? C by lambda here c cube. Okay, this c cube will cancel out. Here lambda cube and here lambda square is there. So total lambda to the power of 5, right? So, and 1 by e to the power of hc by lambda kt, lambda kt. So here one more, in the last expression we have c also, right? Yeah, okay, no problem. So here one c is there, right? Here one c is there, you write here c. Okay, then minus 1 d lambda. This is the expression in terms of what? If you write
Wavelength.
wavelength, the e of lambda is called 8 pi hc by lambda to the power of 5. Okay, 1 by e to the power of hc by lambda kt minus 1. Okay, this is the energy density or emitted radiation from the black body. From the black body you can write in terms of wavelength. Okay, just we are converting frequency in terms of wavelength. Okay, it is easy conversion. Just your only step is here, you know, nu is equal to c by lambda. Just you derive this one, d nu minus c by lambda square d lambda. Just you substitute, then you will get the expression in terms of wavelength. Okay, now we got the expression for Planck's radiation law. Okay, now what we'll do here, we will plot the graphs. Okay, we will plot the graphs from this expression. First, E of nu is equal to what? 8 pi h nu cube by c cube into 1 by e to the power of h nu by kt minus 1. This is what this expression, Planck's radiation law, right? Planck's law. Okay, this is Planck's law. And second one, E of nu, suppose this is the Planck's law we got. Suppose we will take a two special cases. Okay, there is a other laws also there. When we started the black body radiation problem, Rayleigh also tried this problem, and Weins also tried this problem, and also Stephen Boltzmann also tried this problem. Okay, from this Planck's law, they are unable to solve the complete problem. Okay, they are unable to explain the complete black body radiation. That's why Planck came and he proposed some postulates and he successfully explained the black body problem. Okay, from suppose case 1, we'll take from this case 1. Okay, this Planck's law explained completely. So using this Planck's law, can we able to derive the Rayleigh and Wien's law? We'll see that one. Okay, what is this Rayleigh's law explained? Rayleigh's law explained lower frequency side, that means higher wavelength, right? Higher wavelength. Rayleigh's means low frequency range, right? Low frequency range. Low frequency range. Low frequency means what? Frequency is very less. H nu by this, just a second. Low frequency means H nu by kt very much less than 1. Okay, very much less than 1. That means this term we can neglect it. Or this is, or you can write this one. What is the H nu by kt minus 1? How you can write this one? E to the power of h nu by kt, how you can write? So just before this one, just you know what is the expression for e to the power of x? You know, right? Expression, this expression. So e to the power of x is called 1 plus x square, like that, right? X square, like that. So we are taking low frequency means only these two terms we have to consider. That means 1 plus e to the, this is same. Okay, h nu by kt. Okay, h nu by kt plus here also square with, sorry, that note is gone. Just I will roll it again. So we are just what we are doing here. So from the Planck's law, we are deriving the Rayleigh's and Rayleigh's law and Wien's law. Okay, Rayleigh's and Wien's law we are deriving. Okay, so here, what is the expression for e to the power of x? Anyone? 1 plus x square, like this, so on, right? like this one. Here also this is like that only. Okay. So now we will expand this expression 1 plus h nu by kt, h nu by kt. So we will neglect higher order terms. Okay, here minus 1 is there. So this minus 1 and this plus 1 will cancel out. What we will get? H nu by kt we will get. So in case of low frequency, this term frequency is very less compared to 1. This h nu by kt is very less than 1 or very smaller value. Okay, that case this e to the power of h nu by kt minus 1 equal to h nu by kt, h nu by kt. Okay, simply you substitute this value here. Okay, this value here. Now what is the what we'll get? We'll see. Okay, h nu 8 pi h nu cube by c cube, and what is the value here? E to the power of h nu by kt 1 by h nu by kt, right? 1 by h nu by kt, right? So in this expression, just we will rewrite this expression. Okay, this nu and this nu will cancel out, and here what will remains? H will cancel out. 8 pi nu square by c cube into kt, right? Into kt. This is what expression? Rayleigh-Jeans expression.
Rayleigh.
Rayleigh genes, Rayleigh and genes, two scientists, okay, expression, okay, or la, whatever you can say. So this is just we have not derived this complete expression, but this is also having some separate derivation, but we haven't solved this one. From the Planck's law only we have derived. Okay, so Rayleigh-Jeans law explained in case of low frequency region or in the higher wavelength region, that is higher wavelength means what? IR region, infrared region. Okay. So, but according to experimental, this religion is, this is theoretical, right? According to this expression. But experimentally, this law able to explain UV region only. But here from this expression, what we got? This is explaining IR region. Okay. From the theoretical, this law is explaining properly IR region, but experimentally, this law is properly explaining UV region. So that is what we are calling a UV catastrophe. UV catastrophe. This is okay. Some error in the and error in the result. Okay, that means some UV error in the results. Okay. After that, now we have derived the Rayleigh-Jeans expression from the Planck's law. Again, case 2, this is low frequency range. Suppose in a high frequency range, case 2. Let's solve in case 2, high frequency range. Okay, high frequency range. So Wein's law explained in the high frequency range only, right? Properly. After this one, we will plot the graph. Then you will clearly understand how which law is explained, which region. Then you will understand clearly. Now see here, e to the power of h nu by kt. Okay, here e to the power of h nu by kt. Okay, much greater than 1. Much greater than 1. So you can neglect this one. This is very high value compared to 1. So this value, you can neglect this value in the Planck's expression. Okay, here you have expression, right? In this expression, first term is very large. So you can neglect this term. Suppose this term is 1000. This term is 1000. First term is 1000. So this is maybe 1. So in that case, you can neglect this 1. Okay. So like that, we are neglecting this 1 in the Planck's expression. Now what we will get final expression? E of nu is equal 8 pi h nu cube by c cube 1 by e to the power of h nu by kt. Okay, here minus 1 is there. We are neglecting this term, right? We are neglecting this term. So which law this one? This is the Planck. What we got now? This expression. Okay, this is the Wein's law. Okay, Wein's radiation law. From the Planck's law, what we got now? What do we explain? Wein's law and Rayleigh-Jeans law, we have successfully derived the expression. Okay, Rayleigh-Jeans and Wein's law. This law explained in higher frequency side. That is, higher frequency means what? Higher frequency means what?
Low wavelength.
Lower
Low
wavelength.
wavelength. That is UV region, right? UV region. This Planck's, this Rayleigh's law explained. Rayleigh's law explained lower frequency, that is IR region. Lower frequency means IR wavelength, that is IR region, infrared region. This Wien's law explained low wavelength side or higher frequency side, that is the UV region. UV region. Okay, now we'll plot the graphs. This is also have derivation, but we haven't solved. Okay, just now from the Planck's law we derived Wien's law and Rayleigh's law. Okay, now we'll plot the graphs. Okay, we'll plot the graphs. Just we'll see. We'll take one more page. Okay, now this is the radiation density on the y-axis, and the x-axis we are taking frequency. We are taking frequency. Okay. This is very important plot. Just you note down. Okay, this is radiation, emitted radiation from the black body. Okay, radiation density also you can say. Okay, radiation density from the black body. Okay, Planck's law explained throughout the spectrum. Okay, throughout the spectrum like this. Okay, this is maybe 800 or like that. Okay, this is the visible region, and this is the visible region. This is the what region? This one IR region. This is UV region. Okay, this is in terms of frequency we are taking, right? Frequency we are taking. So you can clearly see this expression. We'll go to the next previous page. Okay, here we will see this one. No, not this one, right? This one is not previous page. Okay, here see this one. Rayleigh's law, how it is depending? E of nu depending on nu square, right? Nu square, how it look like? If it is nu square, how it is look like? How, what is the parabolic equation? Parabola. Hello? Hello? Parabola equation. What is the parabolic?
Y square equals to x.
So how it is looking like? This Rayleigh's, this one. E of nu is also square, right? The page is gone somewhere. Okay, it is also Rayleigh's law. It's depending, I am writing again here, 8 pi nu square by c cube into kt. So how you will draw this expression here? See, this is Planck's law explained. This is visible region, and this is which region? UV, right? This is IR. So we are taking scale in frequency. Okay, frequency. So please mute. Okay, this is radiation density or whatever you can take. Okay, radiation. So this is depending on square. Suppose y is called x to the power of n. What is the curve? You can write like this, right? Anything you can write like, you can draw like this, right? Y is called x to the power of n. How will write the curve? Is it correct or not?
Yes, sir.
Suppose y is called x square. Y is called x square. Also you can write this way, right? Y is called x cube. Y is called x4. You can write this way, right? Curve. You can draw the curve like this. Okay, here also it is depending on square of the frequency. So if you draw the curve for this one, Rayleigh gene, it will come like this. So here it will extend up to infinity. This is Rayleigh gene's law. Okay, Rayleigh gene's law. Okay, and similarly that one also Wien's law also depending proportional to nu cube, right? Proportional to nu cube. Wien's law. Okay, this is Rayleigh's law. This is Wien's law also proportional to nu cube. You can draw like this also. This one also. This one also like this. Okay, this is Wien's law. So here see This is Planck's law. Okay. So Planck's law, why it is not extending infinity? Why it is not extending infinity, but only religion Wien's law is extending infinity, but religion is not extending infinity. Why? Because in the formula, if you see this clearly formula, 8 pi nu cube by c cube into 1 by e to the power of h nu by kt. Here minus 1 is there. This minus star protecting to extending this infinity. So this is restricting to this radiation, this curve to only particular value only. Okay, because of this minus 1 it is not extending to infinity, but this religion's law and Wien's law is extending to infinity. That means what does it mean? So here x-axis you have frequency, right? X-axis you have frequency, and y-axis you have what? You have y-axis you have radiation from the black body. So one thing I want to ask you, from this graph what do you observe? Here on the x-axis frequency we have taken frequency. Here y-axis we have taken radiation density from the black body or emitted radiation from the black body. So this religion's law and Wien's law up to particular frequency it is explaining properly. After that it is extending infinity. Okay, this Wien's law also at higher frequency and that is UV region. Okay, up to if you come from higher frequency to lower frequency up to particular frequency it is explaining properly. After that it is reaching to infinity. So what does it mean? What does it mean? Anyone please you see clearly, observe the graph. Y-axis what we have? Emitted radiation. X-axis frequency. So what you can conclude from this graph? What is your observation from this graph?
It does not explain complete spectra.
Yeah, one point is that one. Next, why it is not explaining? One point is that one. So one more thing, and anything else? Anything else? See here. Okay. See here. Up to here, y-axis means what? Radiation, emitted radiation, right? Up to this frequency, up to here, it is okay. Some radiation is emitting, but after that, the emitted radiation reaching to infinity. Is it possible? Suppose if you have any black body, you are heating that black body, it will emit certain amount of radiation, but it will not emit infinity radiation, right? Isn't it? Is it possible? Is it possible?
No, sir.
No, sir.
Only even if you heat any body, any material, it will generate certain amount of heat radiation only, right? It will not emit infinity level of radiation, right? Infinity amount of radiation it will not emit, right? So if you use this religion's law, what is they telling? What is Wien's law? If you use Wien's law, religion law, they are saying up to particular frequency, it is emitting certain amount of radiation. But after that, from the black body, infinity radiation is coming. But it is not possible, right? That's why this law, Wien's law and religion's law, could not explain properly this black body radiation. So Planck's law, what they have done, but in the Planck's law, it is not extending infinity. It is reaching maximum value. After that, it is reducing, right? It is forming a curve shape. But religion's Wien's law, it is extending infinity. So infinity radiation cannot emit from the black body. Cannot emit from the black body. That's why this Wien's law and religion's law could not explain complete black body radiation. So they are restricted to up to only certain frequency level only. That means religion's law explain only lower frequency range only. Only lower frequency range correctly explained. After that, it is emitting. This is not correct, right? Here also UV this Wien's law also explained in the higher frequency range only, up to higher frequency range. Beyond that, it is not explained properly. This is not right. Okay. So, but Planck's law explained complete black body radiation. Okay, if you change the temperature also, you are keeping some constant temperature. If you increase also, this law will follow, right? If you increase, suppose here you are getting the this curve, okay, at 2000 Kelvin. Okay, if you increase the temperature, the intensity will increase, right? Intensity will increase, maybe 3000 Kelvin. But this curve shape is same. Curve shape is same. This should not go infinity, right? That is why this Planck's law only explained properly. Okay, you got it right. A difference between Rayleigh's, Wien's, and Planck's law.
Yes, sir.
Yes, sir.
Yeah. Anyone explain Rayleigh's law? What is he explaining? What is the this thing? What is Rayleigh's law explaining here? Or Wien's law?
Explains about high wavelength and low frequency range.
High wave. Yes, very good. And Wien's law?
High frequency and
High
low
frequency and low wavelength.
Yeah, very good. Okay, that is you. Low wavelength means UV region. High wavelength means IR region. IR means infrared.
Infrared range.
UV means ultraviolet. Very good. Very good. Okay. But Planck's law explained
explains
Visible.
complete
yeah.
complete spectrum. Okay, UV to IR region. That is the main difference between these three laws. Okay, this observation is very important. You have to draw this plot, then only it gives the completeness of the radiation law. Okay, Planck's radiation law. Okay, now this is topic is over. Next we will go to the very important topic, photoelectric effect. Okay, before going to the topic, just I want to make you understand one thing. Okay, Planck's proposed? What Planck's proposed? What are the postulates of Planck's postulates? Or what he proposed? Did you remember last day class? So first one,
Behaves as
atoms.
harmonic oscillator.
Yes, that good. Okay, that's good. Harmonic oscillators. Okay. One thing. Second one, energy is quantized. Yeah,
And
very good.
decreases.
Very good. Energy is quantized, and that is in terms of h nu, integral multiples of h
Integral
nu.
multiples.
Okay, this quantized and discrete energy, quantized and quantized and discrete amounts, what we are calling discrete energy amounts, discrete energy we are calling a quantum energy of quantum or quanta, you can say whatever you can say, quanta or energy quanta. Discrete amount of energy. When light interacts with matter, it releases energy in the form of discrete amounts. The discrete amount we are calling a quanta. These are three important postulate he proposed. Okay, now see, suppose Einstein also proposed, what he proposed, light also it's a like a teeny particles, or it is a photons, teeny particles, he proposed a photons. Okay, now this is also quantized and discrete, but what is the difference between discrete and continuous energy? Suppose discrete and continuous, but suppose you are seeing light. Okay, you are seeing light. How you are seeing? It's a discrete means it's a discontinuity manner. Okay, discontinuity. But how you are seeing light? Suppose in your home, if you switch on the lamp, light is coming, right? From the bulb you are seeing the light. But how that light is coming? It is continuous manner or discrete manner?
Continuous.
But how these are proposed? It is a discrete. So suppose how many photons will come, suppose per second in a light? That light is also looking a continuous, but these people are proposed it is a discrete. So see here what is happening here. With human eye you cannot observe how many photons are coming, or discrete or continuous, you cannot identify. Okay, so if some light ray is coming, stream of photons is coming per second in the light, about 10 power 18 to 10 power 19 photons will come. Okay, in our light we are, once you switch on the lamp, we can see 10 power 18 to 19 photons can emit within a second. That photons can travel. Okay, that much photons will come. So here see, suppose here see, if you throw a cricket ball here, if you throw a cricket ball, how you will observe, what is the trajectory? If you throw a cricket ball, it looks like this. Okay, like this, maybe like this. Okay, but here ball, every point it will move, right? Every point it move like this. But as a whole, you can see a wave. But if you see individually, it is a discrete, right? It's not a continuous. It's like a particle, it will reach. Like that also, here photons also travel like this in a discrete manner. In a discrete manner. Okay, suppose, and also atoms energy levels also having he proposed energy levels. That means discrete energy levels means what? Here, suppose you have any atom, here energy levels are separated a some distance. Okay, this is ground state energy, and this is excited state energy. This is second excited. This is, suppose, let's take a nth state. Okay, this is the simple energy states of a atom. Suppose if you take any suppose harmonic oscillator or anything, how it is look like continuous energy? It's like this, right? Potential energy is called half kx square, like this. Here potential energy is, it's a some separated distance is there. This is the discrete energy system. This is discrete. These are equally separated. These energy levels are equally separated. But here there is no separation one step to other step. There is a continuous. This is continuous energy system. Okay, this is discrete and this is continuous. So in the ladder also, in our home, you can see ladder also, it's a same steps, equal steps are there. Say here we will see some example to understand this one. Suppose one person is there here, he is climbing a some hill. Okay, here he is climbing some hill. Okay, right? At the same person here is climbing a some floor here. Okay, it's like a equal steps. Okay, is climbing here steps. So how you will get here energy? Suppose each step width is h. Here also some height is, step height is h, some height is. What is the potential energy here? What is the
half
potential
into kV square.
of here? Here what is the, suppose this is ground. This is ground. Here you have some object. What is the potential energy of this object? Suppose some h.
0.
It is some h height is there. Some h height. mgh, right? Not 0. mgh, right? Isn't it? What is the potential energy? Before that, what is the potential energy? Potential energy means if suppose some object is on some height, we suppose we keep on some object on some height, so that object is having some potential energy, right? Here also this person having some energy of mgh, right? mgh. But how this will increase? Suppose this person is here. What is the potential energy? Here suppose this is height h and this is height 2h, right? So first person, this second person. First person having energy 2 mgh. This second person having 1, 2, 3, 4, 4 mgh, right? 4 mgh. So here how the energy is increasing? How the energy is increasing? Only step by step, equal number, right? Equally increasing, right? How it
Yes,
is
sir.
increasing?
Equally.
Yes,
Only
sir.
only h plus only adding to the this person. So that means energy is discrete. This here energy is discrete. Here it is, there is no chance of half h, right? Only h only increasing. There is no chance of half h, right? So here energy is at the finally you will have n mgh, n mgh. That means here equal amount of energy is increasing. But here this person, we don't know how much energy is increasing. Suppose person is here, what is the energy? We don't know. Suppose person is here, what is the energy? We don't know. Suppose person is here, what is the, we know energy, but how much amount of energy is increasing, we don't know, right? Here half kx square. Okay, it is some distance, or some distance is traveled, or he climbed, or he climbed some distance, he climbed. Okay, but here we know clearly it is increasing. Discrete means equal amount of energy is adding, or increasing or decreasing. But continuous means there is no particular amount. It's a random value increasing or decreasing. That is the difference between continuous and discrete energy system. So in every atom or material, we are having a discrete energy levels. But here, suppose if any object is there in classical generally, that is we are having this type of continuous energy. But if you take any atom, we are having discrete energy. So using this example, you can understand what is the discrete and continuous energy. Okay. Now we will go to the photoelectric effect. Is it clear, everyone? Difference between this. Just you just correlate. Just you can see in your ladder also in your home. Steps are how the steps are equally fixed, right? They will fix equally. This is also some discrete energy levels. Similarly, we have in atom also energy levels are equally distributed. Equally distributed. These are also discrete energy level. Now we will see the photoelectric effect. This is very